Hi, this is Mr. O'Rourke, and today I'm going to talk about structure and properties of an atom. Now, first thing we want to look at is that we have three particles in an atom. We have electrons, protons, and neutrons. Okay. First thing that we're going to look at are the protons and the neutrons. Now, the protons and neutrons are pretty much identical. Okay, identical in almost every way except for the charge. Now, protons have a positive charge. Neutrons have a neutral charge. The masses are pretty much identical as well, although the neutron is slightly heavier than a proton. It's negligible, but when we all come down to it, looking at it, it's from the interaction of the quarks and gluons within the protons and neutrons that give it these qualities. Not important right now. What we need to understand is they're both about of equal mass, identical in pretty much every way except for the charge. They make up the nucleus, those two particles. Now, those two particles that are found in a nucleus means all the mass is there. Electrons are nearly massless. We'll get to those in a minute. It's where all the mass is found. Also, that's where only positive charge is found. So the nucleus is always positively charged. One thing that we have to kind of wrap our minds around is that if there's more than one proton in there, since they're both positively charged, they're going to want to repel, get away from each other. Okay? We can think of the neutrons as the glue that holds the nucleus together. Okay? So when you get something like helium, a light element with two protons, you need two neutrons in there to kind of stick it all together for it to be a stable type of atom, to keep them together, to keep it from breaking apart. So as you get heavier and heavier, that electric repulsion keeps building up and starts getting very powerful. Okay, as you get bigger and bigger in the nucleus, you need more and more neutrons added on. Once you get up to uranium, which is the heaviest natural element, you have to have so many neutrons on there to keep it together that it's radioactive. Okay, you have 92 protons in there, and you have 146 neutrons holding that nucleus together. Anything heavier than that, you put another electron in there, the electric force becomes strong enough to overcome the strong nuclear force that are holding these neutrons and protons together, that it will radioactively decay into two lighter elements. Okay, so there is a limit to where the electric force of repulsion overcomes the nuclear force and the atom will split on its own. It's called radioactive decay. So there is a limit to where we can go with your protons and neutrons. Okay, there's always some kind of a limit. Talk about the electron. The electron, when we look at its mass, compared to a proton or a neutron, it is 10 to the negative fourth smaller, which is about 10,000 times. Okay, a proton and a neutron are about 10,000 times more massive than an electron. So much more so, electrons aren't counted into the mass of the atom at all, especially for our purposes here. Now, the charge is a negative one. This is opposite that of the proton. It's exactly opposite. Even though the masses are vastly different, the charges are not. They're exactly opposite. One electron is exactly equal and opposite to that of a proton. So they would cancel out the overall charge. So if you have the same number of protons and electrons in an atom, the overall charge is 0. If you have 10 protons in the nucleus of an atom and you have 10 electrons, 10 pluses and 10 minuses, your overall charge is 0. So it's a nice, stable, kind of boring atom that you have when you do that. So that's the play of the electrons, protons, and neutrons. And when we look down here, we can kind of see what it is. We have a nucleus that's positively charged with protons and neutrons kind of holding it together at the center. Around the outside, the electrons are zipping around. The current model is the electron cloud model, which is a little bit too advanced for middle school students to really delve into. As we get into high school and college, you'll get more into that and what's going on. We'll be using the more familiar electron orbital diagrams and stuff in order to count particles and see what's going on with them. It's a little easier to wrap your head around before you get to the more complicated electron cloud model. Okay, a good foundation, and the other models will allow you to get to that model. From here, we'll start talking about the periodic table. And the periodic table can basically tell us, in general, how many protons, neutrons, and electrons an atom will have. Okay, so right here, we have our periodic table. And the way it's arranged is by atomic number. Okay, atomic number 1, 2. Okay, then we go down to the next row, 3, 4, 6, 7, 8, 9, 10. Go down to the next row, limit 12, up to 18, 19, 20, 21, 22, all the way up to 36. And you keep going across. As you go across, you will count up in order all the way up into the heaviest elements. Now, one of the things that throws people off is that sometimes you have that double bar down the bottom that you can see in certain kinds of periodic table. These elements, all that they're down here, actually go in here. It's like you want to break off these first two columns, spread them out. I have a picture of what periodic table with that section that's usually down here put in there. So you have your first two columns, these go across, and then you have your other ones here, the bigger section up here, you have your helium up there, and your hydrogen and helium. Helium's usually over here. So this is what it would look like if it wasn't broken apart. Instead, this is usually what we will see. Okay, that down the bottom. They're not really used too much. But we'll talk about that a little bit later as we advance through it. First thing we want to look at is, how do we read the tiles? Now, by looking at a tile, it gives us information. It gives the atomic number, atomic mass, your element symbol, and your element name. Not all periodic tables will have the element name at the top, but some of them do. The atomic number is always equal to the number of protons. Always. That never changes. It's always equal to the number of protons. Now, in an electrically neutral atom, the number of protons and the number of electrons are going to be equal. If the overall charge is 0, they will be equal. So it's kind of easy to see it. So the atomic number is going to equal the number of protons and electrons in an electrically neutral atom. Easy enough. In order to get the number of neutrons, we have to look at the nucleus of the atom again. It's the number of protons and neutrons combined together to give us the mass, the total mass. If we know the mass of it and we know the number of protons, the difference between them will give us the number of neutrons. So 35 minus 17 equals 18. So in most chlorine, we have 18 neutrons in it. That is the most common form of chlorine. We see the number here is a decimal. Now, what we're going to do is we're going to round to the nearest number. Okay? There are no such thing as 0.45 neutrons or protons. We can't have that. But what this is saying is some chlorine has 18 protons and some have 19 protons. Okay? Now, when we look at nature and we average them all together, the average mass sometimes is some of them are 36 and some of them are 35. When we add them all together and we average it out, we come out with an average mass of 35.45. And that's just because the number of neutrons can vary among atoms. So, but the way we are going to do it, unless otherwise stated from the periodic table, we'll round to the nearest whole number and we will subtract the protons from the atomic mass to get the number of neutrons. Okay, so for hydrogen down here, we have an atomic number of 1, which means 1 proton, 1 electron. Atomic mass is 1.01, rounded to 1. 1 minus 1 is 0. This means that some hydrogens actually have a neutron. Okay, about 1 out of every 100 hydrogen atoms have an atomic mass of 2. Okay, so when we average it all in, we round it down 1.01. Oxygen. Atomic number is 8, so protons and electrons equal 8. Atomic mass of this one is 15. 15 minus 8 is 7. There's 7 neutrons in this form of oxygen. Most oxygen have an atomic mass of 16. So 16 minus 8 equals 8. So most oxygen has 8 protons and 8 neutrons as well. Iron here, 26 is the atomic number, 26 protons and electrons. Atomic mass 55.84, round that off to 56. 56 minus 26 is 30 neutrons. Not too bad. Nitrogen, atomic number 7, 7 protons, 7 electrons. 14 is the atomic mass, 14 particles in the nucleus. 14 minus the 7 protons, you get 7 neutrons. The last one, gold. 79 is the atomic number, so 79 protons and electrons. Atomic mass is 196.97. Round that up to 197, and you get 146 neutrons. Okay, 197 minus 79 is 146 neutrons. So, there we have it. That's the quick, easy way to kind of see how the periodic table is laid out by atomic number. Atomic mass is on the bottom. That's how you figure out the atomic mass, or the number of neutrons, by subtracting the number of protons from the mass. You get the number of neutrons. Also, the number of electrons will be equal to the number of protons in a balanced atom. If you have any questions, you can ask me in class, shoot me an email, and I'll see you next time.